Let's talk about a concrete astrophysics application of angular momentum conservation. So certain stars, which are actually slightly more massive than our sun, maybe 2 to 3 times more massive than our sun, will eventually run out of things to burn, like hydrogen or helium, and so they'll start collapsing by trying to burn other things. And burning of after the burning of iron, they can still burn things, but after iron, they cannot. So they collapse into this very dense, compact object known as a neutron star. It's entirely made up of neutrons. That's why it's called a neutron star. And beyond the neutron star, there's of course the black hole, but we're not considering that. So the principle of angular momentum conservation still applies despite all the complicated physics that's going on. I'll tell you one or two caveats about this conservation when we actually do the problem, but that's what we're going to use. That's our line of attack. So the initial angular momentum is I sub I, the initial moment of inertia of the star before it collapsed, times its angular velocity, and the final angular momentum is IF times omega f. Notice that the direction stays the same because angular momentum is a vector. The initial moment of inertia can be taken to be that of a solid object. There's no reason to get complicated here. So it's a solid sphere of radius r, sun. The symbol for sun is circle with a dot. And the final moment of inertia is 2/5 times mass. And this is the caveat I was talking about. We're going to assume that this entire mass becomes a neutron star. In reality, that's not true. A good deal of that mass is lost. So we're not getting into those details at all. And then if you substitute those things over here, you're going to get omega final. If I set these two equal, I'm going to get omega final is I initial over I final omega initial. And so if I make those substitutions, let me do it here. IF is 2/5 m r sun squared divided by 2/5 m r neutron star squared times omega naught. You see that a number of things cancel out, leaving us with just this. Now omega is a little more abstract than the period of rotation, so I'm going to use the period instead. Omega by definition is 2 pi over t because it measures the time, t measures the time taken to go 2 pi around, and that's precisely the definition of omega. It's angle covered, which is 2 pi radians, divided by the time taken, which is called the period. So let's write this whole thing in terms of the period instead. I'm going to get 2 pi over t final is equal to r sun divided by r neutron star squared times 2 pi over the initial time t naught. So let me solve tf. If I cancel out those 2 pi's and then I invert this thing, so I get r ns over r sun squared times t naught. Now I do know that the density, not the density, the time t naught for something like the sun, stars like the sun, is about 1 month. Big stars don't rotate very fast because they're nuclear reactors, and you cannot have a fast rotating nuclear reactor. In fact, that's why stars form planets, so that they don't have to rotate that fast. Now I know that 1 year is pi times 10 to the minus 10 to the 7 seconds. That's one of those things I like to remember about units. So 1 month would be pi over 12 because there are 12 months in a year. Let's go do this calculation. Now the only problem with this calculation is I don't want to look up these things. First of all, the radius of neutron star really depends on different starting conditions, so it's best to write everything in terms of density. So let's try to get an expression in terms of density. Remember, the density is mass over volume. So we do know that the final star is made up entirely of neutrons. So what I'm going to assume is all these neutrons are going to be tightly packed next to each other, but it's safe to say that they don't come closer than the box containing them. So it's enough to think about the diameter of the neutron and make a box out of it to put the neutron in, and we can find the density like that. So the density of the neutron star is just the mass of a neutron divided by that diameter cubed. The mass of a neutron is about 1 AMU, which is 1.67 or 1.7 times 10 to the minus 27 kg. And the diameter of a neutron, I know that the radius is about 1 Fermi, which is 10 to the minus 15 meters. So it's going to be 2 Fermi, but I'll write it as 1.7 Fermi. So Fermi was a great physicist, and he used to do all these calculations on the back of his mind. So he was very famous for that. Now I'm cubing it, right? So one of the factors of 1.7 will go away, and I have 1.7 squared. Well, I know the square root of 3 is nearly 1.7, so that's going to be 1 over 3 then, times 10 to the minus 27 divided by 10 to the minus 45 kg over meter cubed. So you can already see these numbers are amazingly huge. That's 45 minus 27, which is 18 kg per meter cubed, which can be written as 3 times 10 to the 17 kg per meter cubed. Now these equal signs have to be taken with a grain of salt. These are all approximation signs, and especially here I'm going to neglect the 3, because any number less than 5 I'm going to write it as 1 for my order of magnitude calculation. So it's a tremendous density. Now I also know that stars are more or less like water. That might be a strange statement, but the density of most stars that are shining currently is not much different than that of water, average density that is. So that's 1 gram per cc, and if you write it in kg per meter cubed, that's 10 cubed kg per meter cubed. Remember, a meter cubed is the size of a large fish tank, so it can hold a ton of water. So what I'm going to do is replace the radii calculations with density calculations. Now remember that mass of the star is equal to rho star times the volume, which is a sphere, we are assuming, and the mass of the neutron star is going to be the same. Again, that plays into our assumption that nothing is lost in the collapse process. So if you look at this, I'm going to get the radius of the neutron star divided by the radius of the sun cubed equals rho sun over rho neutron star, and that gives me RNS over R sun is equal to rho sun over rho neutron star to the power 1/3. So now we are all set for this calculation of the final rotation time of this neutron star. Let's continue this calculation here. So TF is going to be rho sun over rho ns. Now I have squared and a 1/3, so it's going to be 2/3 T naught, which is 1 month. I'll write that in the next step. So this is going to be 10 to the 3. I won't write units on the density because they cancel out. 10 to the 17, 2/3, and that's pi over 12 times 10 to the 7 seconds. That's going to be 10 to the minus 14 squared, so that's 10 to the minus 28 divided by 3. Now pi is 3 between friends, so that's 1/4 times 10 to the 7 seconds. 3 divides 27, so I'm going to think of that as 27, so that makes it 10 to the minus 9. So you can already see some approximations are being made. And 1/4 I'm going to write as 0.3. It's 0.25, but I'll write it as 0.3 times 10 to the 7. And that's nice because I can simplify this. It's 0.3 times 10 to the minus 2 seconds, which can be written as 3 milliseconds. So you can see it's really, really fast, the rotational speed. That's why these are called millisecond pulsars in the astronomy community. Well, in the previous video, I showed you that the kinetic energy ratio can be thought of as the inverse moment of inertia ratio. So if you've not watched that video, you should please do so. This is the one where the satellite unfolds its solar panels. So that's I initial over I final. And so if I substitute for the initial moment of inertia and the final moment of inertia, I'm going to get R sun over R neutron star squared. And that's the opposite, the inverse ratio of this. So all I have left to do here is invert this one. Fortunately, I have not messed with this part much. So if I invert 10 to the minus 9, I'm going to get 10 to the plus 9. So that's a tremendous, it's a billion-fold increase in energy. Where does this energy come from? It turns out it comes from gravity. So the total mechanical energy in any process is conserved. So TMEI equals TMEF. The total mechanical energy initially of the star was the gravitational potential energy of the star plus the rotational kinetic energy of the star. And the final total mechanical energy is the gravitational potential energy of the neutron star plus the rotational kinetic energy of that neutron star. Now there's some bit of physics which is a little bit beyond the scope of this course, but let me just write it anyway. The kinetic energy is 1/2 mass times, it's a moment of inertia times omega squared. The gravitational potential energy is this is the part that's slightly beyond the scope of this class. It's given by 3/5 Newton's gravitational constant times the initial mass divided by the initial radius. So that's the part that is squared. That's the part that's the 3/5 part requires some calculus, because essentially you're trying to find the gravitational potential of an object on itself. So each mass point interacts with other mass points. So it's called the self-gravitational potential. So that requires a little bit of calculus to do. Other than that, it's just some number less than 1. Not a big deal. That's equal to 1/2 times the final kinetic energy minus 3/5 gravitation constant times mass of the neutron star squared over the radius of the neutron star. Now the mass of the neutron star and the mass of the sun are about the same, so the numerator is the same. But what about the denominator? The radius of the neutron star is going to be incredibly small. You notice that the radius of the neutron star is approximately 10 to the power 4.5 times smaller than the radius of the sun. So just to give you an idea, the radius of the neutron star, of most neutron stars, are about 10 kilometers. So that's the size of Rochester. It's really small. So this is going to be a very big negative quantity. And that's going to be just a somewhat negative. And let's just say that's somewhat positive. So you have somewhat positive plus somewhat negative, and you have a very big negative, so you need a very big positive here. And that's the reason why this gravitational potential energy that's feeding into this system, it's getting so negative that it has to go somewhere, and it goes into the spinning up of the neutron star so that the left hand side and the right hand side can be equal.